Alright, this is going to be chapter 12 and 13 study guide. I already went over, there's already a video up for chapter 12 for all the math, so we're just going to go through some of the definitions in chapter 12 and then do the math for chapter 13. So, first thing for chapter 12 you need to know is solutions, suspensions, colloids. You need to know sizes, examples, and explain what they are. So you need to know all about that. The Tyndall effect. There's a nice table 2 on page 404. Would be a good thing to know for that. The Tyndall effect for colloids. So that's on page 404 as well. That's fog reflecting light back at you. Be able to explain that and what it is and why it does what it does. Electrolytes versus non-electrolytes. And then factors, right? 3 factors that affect the rate of dissolution or how fast something dissolves. Right? Agitation or stirring, heat, or increase surface area. Right, remember, because the only part that dissolves, if I have a cube of sugar and water, the only part that actually gets to dissolve into the water is the outer edge, the part that's actually touching, so these sort of surfaces, and all of the stuff inside doesn't get to dissolve. So if I break this down into smaller pieces, or like I crush this sugar cube, now there's a lot more surface area available. Remember, and one reason why stirring helps is because at some point, as this sugar dissolves, the water surrounding it becomes saturated, and that's that sort of very small area, and there's no room. But if you stir it, you move fresh water in, move the saturated solution out, you dilute the solution, and then there's some more room. Saturated, supersaturated solutions based on that worksheet, you should know all about those. Remember, supersaturated is a solution that contains more dissolved solute than saturated, and it's a temporary condition usually because of heat. Henry's law. You do need to be able to explain and know what Henry's law is. Alright, and for it's on page 413. It's usually your soda bottle example. I can dissolve the bubbles in my soda bottle. You don't see the carbon dioxide because it's dissolved and because it's under greater pressure. You release the pressure, I can't dissolve as much gas. It forms into little bubbles and comes shooting out to the top. This is also, so soda bottles, this is also why you get the bends, right? The night you scuba dive, you absorb more nitrogen in your blood than you should. You come up too fast, it comes out. That's on page 413. So you should know all about Henry's law and effervescence on page 413. You should also know the definition of miscible and immiscible. And that leads us into molarity and molarity calculations. You should know the steps on page 418 on how to make a solution of a given molarity. So remember, if I want if I want 1 liter of a 1 molar solution, that means I want 1 liter, this is at the end, right? So I can't pour in 1 liter of solvent. I'm going to have to do something, I want to make 1 liter, I should pour in, maybe half or so. So let's say 500 milliliters, right? Then I pour in the correct amount of my solute. And generally, it's, you're going to have to tell me in grams how many I need, but you have to work that backwards from moles, because moles is what you have in the equation, right? And then that's going to obviously, though it's dissolving, it's going to increase my volume a little bit. And then after that all dissolves, we'll top it off. The final solution has the correct volume. All right, then there's the math. Lots of sample problems starting at page 420. I would work through those sample problems. Molarity, molality. Remember molarity, big M, moles over liters. Molality, is moles of solute kilograms of my solvent. Alright, that takes us into chapter 13. So we're starting with ions. Dissociation is something splitting into ions. Alright, so I have salt, which is soluble, so when it's in water, it's going to dissociate and turn into its component ion parts, and as long as it is in solution, it stays dissociated. Page 437, table 1. You need to know that. There's your solubility rules. You can shorthand a lot of them because a lot of them are sort of come up again, but for instance, if I was to write number 6, so like number 6 says most sulfides are insoluble except for those of calcium, strontium, sodium, potassium, and ammonium. Well, you could just write, sulfides, or just S equals insoluble, or some shorthand that you know, except for, calcium, so Ca, strontium, sodium, potassium, and ammonium. That you could fit pretty tightly onto a piece of paper. So precipitation reactions, net ionic equations, right? So you need to know that. So that's anytime I make a product, I have two soluble reactants and one of my products is insoluble, so there's an actual chemical reaction that occurs. You're going to have to be able to write the full ionic equation for something and the net ionic equation. Okay. Examples start on page 438 in your book is sort of talks about how to do it, and then page 440. Identify the precipitate that forms when an aqueous solution of zinc nitrate and ammonium sulfide are combined. So we've got zinc nitrate, so ZnNO3, 2, because you're going to need to know these charges, plus NH4 NH4 Alright. Well, double displacement says that's going to make ZnS plus 2 NH4NO3. And I have to look at my solubility table, and we're going to figure out that this is in fact solid, it's insoluble, and that is aqueous. So I do have a net ionic equation. The overall ionic equation is Zn, you have to write the charges, plus 2 NO3 minus, plus 2 NH4 plus S yields insoluble solid zinc sulfide. So you don't split it, plus 2 NH4 plus 2 NO3 minus, and I ran out of room, plus. So this is my overall ionic equation, right? So I write that, and then I have to identify my net ionic equation. Well, the only thing they have that's a solid is zinc. All right, so that's a precipitate. It does not stay ionized, so that chemical reaction will actually occur. Well, what's that made up of? That's a zinc with a 2 minus that I forgot, or the sulfur with a 2 minus and a zinc with a 2 plus. So my net ionic equation, or what actually happens, as long as this is in solution, is just this, and you do need to include the solid part, identifying this as a precipitate. Remember, if both of your products are soluble, you have no reaction, nothing actually occurs. Strong and weak electrolytes and the hydronium ion. Remember, hydronium ion, well, this ionizes into H plus and Cl minus. But when dissociation occurs, ionization occurs. It is, I create an ion that wasn't already there, because the hydrogen proton will not sit around alone. It will tag itself to a water. So I actually end up with this. Remember, a weak electrolyte will give a reversible reaction. It doesn't all ionize. It starts to reform. Then we have our colligative properties. We have vapor pressure, changes in vapor pressure. So I have freezing point depression and boiling point elevation. Remember, that's just the change in the freezing point is a constant times some molality. Just remember that often to get molality, Well, I'm first going to calculate that. That's moles over kilograms. And then I'm often to calculate that, I'm going to have to first figure out moles, which is grams divided by the formula mass of that substance, and then I can work backwards to calculate a molality. And also remember that this number is just that I calculate. This is my change in my temperature. So it's not necessarily my new one. If the equation asks you to calculate the change, you calculate that. If it asks for the new temperature, you need to add it to your starting one, either your starting boiling point or your starting freezing point. And remember, if it's not water, I'll give it to you. But you should be able to solve for any of these. But remember the values for water. The freezing constant is negative 1.86 degrees Celsius per 1 mole concentration, and the boiling positive is 0.51 degrees Celsius. Remember, so boiling point elevation, your new boiling point should be a positive number, it should be bigger, and your new freezing point, well, your change of freezing point should be a negative number. It should ultimately get smaller. And then remember, these are for non-electrolytes. If I have an electrolyte solution, then I end up changing this by the amount of the number of moles of ion particles that I would have. So I would take my temperature change times the number of ions, right? So NaCl equals times 2 ions, twice as effective, H3PO4, 4 ions. Something like anytime you have remember, I'll identify other electrolytes or non-electrolytes for you. But remember, something like some sucrose or carbon hydrogen chain, this is a non-electrolyte. This does not split. It's just one. So you got to keep that in the back of your head. All right, again, sample problems in your book. Really good sample problems for ionic compounds for electrolytes on page 454 in your book. And so I would walk through those samples and see if you get the same answers that they did otherwise.